All right, so you've heard the Center of Excellence at Stanford and UCSF, a Cure Accelerator. And it's my real pleasure. In fact, I'm incredibly humbled to be sharing the stage because I feel like, remember Wayne's World? We're not worthy. I don't feel worthy, really, but I will do my best to be up here with Dr. Sung Kim and Matthias Hebrock. And these are two exceptional leaders. They will be the co-directors at each of these prestigious institutions who are joining forces to create this center. Dr. Kim, who's a professor of developmental biology, and if you look on the back, so I'm going to do this relatively quickly because I think it's better to hear from them directly at Stanford, and Dr. Hebrock. And I was when Matthias and I were talking here, I think it's been 15 years since Matthias and I first met. He's now a distinguished professor at UCSF and director of the Diabetes Center there. Each have made seminal contributions to this field. We're talking about two of the preeminent people in the world in driving towards cures for type 1 diabetes. And now we're locking arms together in this JDRF center to try to bring it home. So Matthias and Sung, if you'll come up. Now, the one thing I'm going to say is Sung, it's a special day. It's his birthday. So he's saying, so he's waving more applause. We're not going to sing for you, but we will thank you for taking time away from your family and sharing your vision here. So, gentlemen, thank you. I'm so pleased to be here with you both. And I'm just going to start with my reference to James Shapiro and islet transplantation, which to some degree was an incredible blessing. We've learned a lot from that, but I don't want to say it was a curse, but it set expectations high. And I know that there are folks who have received islets, obviously UCSF, but let's talk about the potential here. Insulin independence, and then how you're thinking about this center addressing what are the barriers in terms of cell source and the immunosuppressants that are needed. So let's talk about what this has showed us the potential and how you think this center then fits in addressing the gaps.
So thank you very much. Thanks for inviting us. It's fantastic to be here. And thanks for all the support for the center that already has come in. We're very, very grateful for that. I'm Matthias Hebrock. I'm at UCSF. I've spent a long period of my life trying to understand how the pancreas forms, and then by extension, the cell that you care about and we all care about, the insulin-producing beta cell. Actually started out by doing this with this young fellow here on my side in this little place.
25 years ago.
Yeah, 25 years almost in this little place called Boston. And then we both moved out here. So and it was up there already, the hope always was that by understanding how we can generate the embryo and how the embryo generates the beta cells, that we can take that information and then replicate this. And taking cells that we now call stem cells, the embryonic stem cells or induced pluripotent stem cells, and then guide them through a long process. In our hands, it takes us 28 days to the point that they become a beta cell. And we've done this over the last several years. Actually, we've been at it, just to see how fast these things go, 12 years. And we now can generate a cell that looks and smells like a beta cell. It's not 100% identical, but it's around 90% identical to what you have in your body. And what that means is that we are now, in theory, have a supply of cells that can be used for cell transplantation purposes. The second part of that is, of course, that even if I give your loved ones or yourself a cell right now that is a beta cell, your immune system has decided to destroy it, and it has done this very efficiently. So the other piece of what we have been working on together with our colleagues at UCSF is looking at the flip side. trying to understand how we can either modulate the cell itself, the beta cells, so that we're giving it a cloaking device, that it cannot be recognized by the immune system anymore, or by moving the immune system in a way that it now tolerates the cells that we're trying to put in. So the cure for me, and I'm going to stop and let Song talk in a second, the cure for me is if you wake up in the morning and you have type 1, and we have given you these kind of cells that I just described, and you really don't care about if you have sugar in your coffee. That, for me, is the cure, and we are working very hard in getting there.
But by the end of this evening, I'd like you to sing "Happy Birthday," but not to me, because of the Center of Excellence being born essentially yesterday, or the precedent announcement. So why don't we start off on that note, because it's, your circadian rhythms are at a kind of low now. Let's just sing "Happy Birthday" to the Center of Excellence, okay? Happy birthday to you. Happy birthday to you. Happy birthday, dear Center of Excellence. Happy birthday to you. So we're here to celebrate the inception of this, and this is like a family. Actually, Matthias, when he got married, asked me to be one of his two best men. So we go way back. I always joke that he wants to be just a little bit extra. So he had two best men. I only had one. So it's really been a long-standing partnership. And just to answer the call, I think we're here because we believe that cell therapy works. And this is borne out again and again in the history of medicine. We replace, without really even thinking about the dangers or the complications of the science, we replace blood cells routinely. Red cells, platelets. I used to do this. We advanced to being able to replace people's whole blood system through bone marrow transplantation. And I think that the Shapiro advance, or the Edmonton advance, which stood on the shoulders of some rather large figures, Ricordi and others, it really showed the community that you could have extended durable islet engraftment, not what had come before, but ever since it was before and after that event. So that, I think, shook people up into thinking that cell therapy could work for islets as well. And we are committed to that in the center. The thing about diabetes type 1, as you know, is that there is not only a need to perhaps address the replacement, matching the person that you give islet replacement to, but also quelling or suspending, eliminating the autoimmune attack. And so the basis of our center, in part, is to address that compelling second pillar, as Aaron said. And in order to do that, we are hoping to rely on combinations of drugs, like you heard about, that were highlighted, that attack the immune cells that are responsible for destruction of islets, but also to help support the engraftment of the islet cells that you transplant. So we need to be able to solve those twin problems of replacing the islets, getting enough of those, and there are many ways to try to do that, but also because of the combined expertise and passion of the faculty at these two parts of the center to address the immune problem, which is to ultimately to dampen or to prevent autoimmune destruction of the islets. So that's I really think that it's about cell therapy, and at some level we call different ages, based on technology, the age of the transistor, the age of the the semiconductor, the age of the iPhone, I don't know, but we've always been in the age of the cell. This is and forevermore shall be the age of the cell. That is really the unit of that we're talking about. So our focus in the center is to protect those cells. So that's my response.
Let me add one more thing, if I may. I think we are at an inflection point right now in biology. There's a couple of things that have happened over the last several years, and stem cell technology is one of them. We actually are now finally can generate the cells that look like cells that people have in their bodies. That was not true 3, 4, 5 years ago. This has changed. But the second part is this amazing technology that I'm pretty sure many of you have heard about. We call it CRISPR. It's gene editing. And if you think about this, it's just an unbelievable technique. Every cell that we have in the body, and we have around 10 to the 14th or so cell in our body, in every single cell we have somewhere in the vicinity of 3 billion base pairs. These are the little units that make up the DNA that essentially encodes everything that we need to make our proteins. 3 billion, that's 10 times more approximately than we have in the United States as people living here. And we can use this technology now, this CRISPR technology, to go in and exchange one out of these base pairs. And not just willy-nilly, anyone, the one we want. And these things now allow us at a level that was just unbelievable like several years ago. I'm saying what we're doing these days is we're taking fiction out of science fiction. And it feels like that because we can essentially modulate these things right now, and we can change the immune system in the T cell just a tiny bit, or the beta cell just a tiny bit. And then we're developing in the center, together with all of our colleagues, the assays that essentially allow us to ask, does this really make a difference or not? And if it does, of course, we're going to further look into this. So this moment in time where I think the technology of the stem cells and the gene editing tools, as well as in immunology, our knowledge in immunology has increased so much. This is just something I don't think we have seen before.
That's great. So now let's talk. Tomorrow I have to go up to Seattle, and I'm actually going to see Cal play Washington. A little rivalry. Occasionally I hear that there's a little bit of rivalry between UCSF and Stanford.
Where did you hear that?
So here we have, it reminds me back when we started the Artificial Pancreas Project, we had some rival groups, and I use the term rival, there's healthy competition in science, but unite and really catalyze significant progress. And here we have 2 powerhouse universities, powerhouse diabetes teams, joining forces. Talk about how you guys worked on the proposal and how you think that'll strengthen and accelerate the work that we're talking about here.
Well, I think Doris Goodwin coined the term team of rivals. You can have a very productive team. I really don't think there's that level of rivalry as there was in Lincoln's cabinet. I think in science, since maybe quite some time now, recognize that we need expertise, and we need to tap into a team of experts and their energy to drive discoveries forward. It's very unusual now to have does anybody know who Robert Hooke is? Yeah, he was a London tool maker who invented a microscope and published what cells look like. We're talking about cells. He published the first pictures of cells. The lone wolf doesn't exist anymore. We work in teams. And so other than trying to dispel this notion by saying we're linked through sort of a virtual marriage, I mean, I've known him longer than his wife, than he's known his wife. We have different things to contribute, but the effort is aligned. So where I think there's an interest in studying the processes in one of the projects, that there'll be a little bit more effort from the UCSF side. If I can take the liberty of saying, to understand the immune process, the autoimmune process in type 1, through some of the powerful methods that Matthias was mentioning, including CRISPR, including in biology the principle of reconstituting or reproducing the phenomenon that you think might be the one you want to study, whether it's through cancer, as Aaron was talking about, or through culture of cells in the test tube. On our side, a little bit more, we have a history at Stanford of using bone marrow transplant and now hematopoietic stem cell transplant to try to achieve the quelling of the immune system attack on an organ. Cell and organ replacement works. There are people now that are part of our center, Everett Meyer and Judy Shizuru. Everett's not here, but Judy was arriving, who have helped to pioneer with Sam Strober and others the concept that you could replace someone's kidney and then give them, matching with that kidney, the donor bone marrow, and then very soon after that, all immunosuppressive drugs can be withdrawn. And so for 20 years and more, they have a growing history and experience of having intact renal function from that transplanted kidney without immunosuppression. That's what captivated me about building this team, and to contribute that idea and work with people at UCSF. We are now collaborating with Kishi Tang and with Jeff Bluestone, using preclinical models to see if that will work not only in that setting, which is only about allotransplantation, but also now in autoimmune models of beta cell destruction. So if you could do that with the concepts that Strober and Shizuru and Meyer have created, that would be a game changer as well, and address some of the questions you were raising before.
So the first thing is, you know, I love UCSF, I love it dearly, but we don't have a football team, so we don't play Stanford. I think if I would show up, they would beat us. But look, I mean, it's not rivals. I think what Song said is absolutely correct. You have, I believe you believe that, you have two powerhouse institutions here in your backyard. If you look around the country, you look around the world, it doesn't exist in a lot of other places. There might be a handful of other places that have that. So for them not to work together would be kind of silly, especially because we're not completely overlapping. Song and I, we have been collaborating on and off for years, for many years, decades now. And we're going to find something that we can work on where he is going to take the lead in something and I'm going to take the lead in something else. So this is perfectly fine. This is how science is moving forward these days. So I hope that essentially, because we have slightly different aspects that we would like to address, at the end, the overall, if you put it together, is much larger than the single pieces. And then lastly, Karen is not going to let us, you know, not play nice. So,
So let's talk about, again, I'll harken back to the AP days when we set out on different approaches. Some people used model predictive algorithms, some people used fuzzy logic. There were different groups. We collaborated, but other people were working on specific tasks that they thought would get to people with diabetes. So one of the questions I got coming in here was, oh, well, Semma was acquired, we're done. I'm a big believer that, of course, we're not done there, or we're not in the clinic and we're not curing people yet. But talk about the value of the different approaches and how your all's expertise may complement in some ways what Dr. Melton may be doing, will be different. And again, the potential for different shots on goal and how important that is, particularly in a time where we're still learning.
So as a full disclosure, I'm on the advisory board for Semma, and as a full disclosure, Song and I both trained with Doug, so we have admiration, and I certainly owe a huge chunk of my career to Doug. So what Doug has been doing in Semma is just fantastic. I mean, there's no way around this. In just, I think, 4 or 5 years, they have developed a company that just was sold earlier this week, and they have a technology that is fantastic. I usually look at this a slightly different way, and because I like cars, I look at the cars. And when the Model T came out, right, it was a revolution. That was something that was absolutely fantastic. I'm not saying it somehow in cells are like the Model T, but in analogy, my car that I used to drive down here is different than the Model T. So what a company like Sema is fantastic at is developing a technology, scaling it up, making sure it works 9 or 9.5 or 9.9 out of 10 times, making sure that the quality is there, and essentially then they're moving something into one product. That's essentially what they mostly are looking for. What we would love to do is we would like to anticipate what the next step is. So for example, can I generate a beta cell that I can give you, and your immune system is not going to recognize this, what I said before, an immune cloaked cell? That would be something I would love to have. Or can I essentially give you a T regulatory cells that Jeff and then the other guys now can generate out of the, well, getting close, out of your human stem cells that essentially would go in and tell your T cells that are about to attack the beta cell, no guys, they actually belong to us, just take aside. So I think what we are trying to do here in academia, and that's where academia is good as, if we are funded, we take the risks to essentially walk into the unknown rather than take something that likely is going to happen and make it really fantastic.
My response to the question would be to amplify on that. We need to have a diverse set of therapies for any given disease. We also need to continue to study the cellular, molecular, genetic, environmental basis of the disease. In medical school, we learn that therapies change, but the pathophysiology is there. So we need to study both. The therapies are going to change and evolve. An example of successful cell therapy is bone marrow transplant, which was invented at the end of the 20th century. It's been around now for over 40 years, but it's by no means a perfect science. We're still studying that. Any kind of therapeutics needs a kind of diversification of its portfolio under development. I guess I would say it in that way too. But I think that we're trying to build off each other's progress, and I think there's great momentum toward doing that so that we can also align our approaches when the time is right.
That's great. I think it's a super important point for the audience that a strength, I think, of JDRF particularly over the last 10 to 15 years is stimulating multiple groups trying to solve problems. And competition drives innovation and it drives acceleration. And, having incredible groups working on different angles to the problem, I think is huge. All right, so I'm gonna have one more question and then folks can ask questions. And the number one question I get in events like this is when? And I'm sure somebody is like, when can I get a transplant? We know that ViaCyte has moved into humans with a macro encapsulation device. I personally, knowing the fraught history of when, 5 years, that old story, but talk about, so I'm not gonna say like it's 2000 and X, but I do think it's important for folks to understand that when we talk science, so our groups, the JDRF scientists and you all, we do talk about milestones and talk about some of the key milestones that you think you'll be aiming to achieve with the center over the next couple of years.
Well, to credit JDRF, they ask us to write down milestones. That's the...
Which we love to do.
I guess that's the stick, or maybe it's the carrot, I don't know. What we haven't yet been able to do in any kind of convincing way, although there are publications from our own members, is to first use cell-based therapies to cure diabetes in the preclinical setting for a long, long time. And that setting, in that preclinical setting, would be to achieve what's called allotolerance. So you get a islet set from an unrelated donor, and it lasts and lasts and lasts. So that's a milestone that I think we're very close to trying to say we're at or achieving in a mouse, which hasn't ever been done before because of pioneering work by people like Judy Shizuru. I don't know if Judy, are you here? Yeah, so you're gonna have a chance to meet her later. There she is in the corner, modestly raising her hand. Raise your hand one more time, Judy. Yeah, so talk to her about her work. I think for us, the next thing in our project is to work with Kishi Tong and Jeff Bluestone and Everett Meyer and try to cure autoimmune diabetes in a mouse with an allotransplant and bone marrow transplant. And that would be amazing. That would be phenomenal. If there was no graft versus host disease in that setting, then you would have broken through two barriers, allo and autoimmune destruction. And that would be, I think that would be a huge milestone. Third for us is to try to develop the regimes, and this is where it gets a little technical, but immunology is this way. You have to clear out space from the bone marrow to put in new bone marrow. And if it's a donor bone marrow, and it engrafts, it grows, that's a state that some people call a mixture or mixed chimerism. If we could find ways to do that safely, ever increasingly safely, and it's already been recently reported that you can do this to then promote tolerance of a heart transplant or transplanted heart muscle. If we could do that, then to the short answer to your question, like who cares about mice? When do we get to the clinical trials? That's what we're trying to do. And I would say everything in medicine and biology is contingent. If you say, when will, what time? Well, it depends what your question is. If your question is if you can find a setting where it's really, really safe, and Judy can amplify on this, if it's really, really safe to give someone purified hematopoietic stem cells and have them engraft, and there is a very different regime than what we currently use because of work by her and others, then we could propose a clinical trial perhaps where we use that as a paradigm for something like prevention, right? I mean, that's the idea, is that you could use it in a different context if it's safe. Ultimately, that's the key, is where's the bar for safety? So I would say mouse, 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 human, human. We're building toward human trials.
So I can give you some of the milestones that have to do with better understanding how the immune system regulates beta cells. As many of you know, there's actually JDRF is supporting this. There's something else in Florida, it's called NPOT, where essentially you have access to tissue samples from type 1 diabetic patients. And what we're seeing by studying these images is that not every beta cell is destroyed immediately. If you have a bacterial infection, the immune system comes in and takes care of it very efficiently. It doesn't happen in the context of type 1 diabetes. So we don't, for example, understand why one T cell goes and is about to attack this beta cell versus the beta cell next to it is protected. So we'd like to understand that, and this is something that I think will allow us to then use this information and modify, using the stem cell technology, both the immune system as well as the beta cell to address this. But I want to briefly push back. First of all, some of you guys know me, I never give you any dates. So that's not going to happen because I think you would be wrong whenever you do it. But let me say one more thing. Do you guys know what's going to happen in 2022? I gave it away. Yes, exactly. It's the anniversary of insulin, right? Insulin is, for me, a wonder drug. I mean, hands down, next to penicillin, that's the one. Insulin is just amazing. Okay, so we have it for 100 years. What have we done? Okay, we went away from pigs and cows, and now we have humanized insulin. That's a huge thing. That was really big. Now we have fast-acting and long-acting insulin. That's great too. But the one thing I want to have is I would be a type 1 diabetes, is smart insulin. Just inject myself with the bolus. Nothing happens until I hit 95 to 100. It gets active. It goes down. When it goes down to 75, perfect. We don't have that. And they had 100 years. What are the guys doing? For the stem cells, you guys know when the human embryonic stem cells were identified? You guys need to read up on this stuff. This is important. 1997. So we're a little bit over 20 years where and up to 2005, where Biocide actually was able to show, to take a human embryonic stem cell and make definitive endo, which is really the first step out of like 20. We couldn't even do the first step until 2005, so the race kind of started in 2005, and now we're in what, 2019. So what we have done, and by we, I mean the field, over the last 15 years and moving this forward to get to a point that we have a cell that looks like a beta cell is amazing. So I think there's a tremendous amount of progress that has been made. And yes, if my son or my daughter would have type 1 diabetes, I would still yell at me and say, do it faster. We have been pretty fast.
All right, well, I am going to see if folks have questions. I mean, these are two of the most important and innovative clinician scientists in the world. Uh, we have a mic. You can just raise your hand and Howard.
Congratulations. This is exciting. Happy birthday. My question is two related questions. One is, how will the great discoveries that you're definitely going to make in a hurry get translated to companies that are going to productize them? And related question is, what is the agreement that you have about that intellectual property? Is it all going to be released freely, or will companies be able to take it and own it and make their $1 billion with it?
Okay, so thank you for that. We actually have a group of supporters who are in the investment community who will look at some of the portfolio that we have at the UCSF Diabetes Center. UCSF has a start out of the box, and I can't speak for Stanford, I assume they have the same thing. We have started tons and tons of companies based on the best idea of our faculty. So actually we are being asked now to do exactly what you say, recognizing that in academia to push something to the point that it becomes a product is someone is kicking me out here, sorry. So we do have this in mind. Yes, the IP will of course be shared if it is co-developed, and we absolutely would like to move these things forward to fruition in a commercial entity when possible.
I think Judy and Everett have started companies around their discoveries, so that's one way forward. So they may come to the fund, T1D fund. That's one idea. There's IP around their ideas. There's also, depending on what it is you're talking about, probably a lot of room for the closed-loop systems that David Moss, my colleague, and Daryl Wilson, my colleague, have pioneered or are continuing to work on for supporting the engraftment of these tissues so that they are in a more stable glucose normoglycemic state. So there are just boundless opportunities, I would say. It's just that's a topic for a whole nother hour. You had a second question? I can't remember what it was.
I was curious how the intellectual property
Oh, yeah.
JDRF
Yeah.
would be in the companies that get created.
So I can answer that, Howard. I think one of the things we do when we grant money is make sure that there's pathways to access and company formation and intellectual property. We have clauses that make sure that it's not used to block. In fact, Dayton Coles really helped us over the years, one of our former board members, craft a number of these policies. The goal is to see these solutions come to the market. And somebody actually pinged me on Twitter today, tagged me and said, because I had retweeted the Semin news, will cures be affordable? And I think that's an important component. Normally, I have a slide that shows the different steps that it takes to bring things to the market. And of course, I alluded to this earlier, we have a healthcare challenge right now in the United States where even insulin is becoming inaccessible to people. That is a completely unacceptable state. So we have a major focus on not only R&D, the research, the development, but also the commercialization aspects, including and all the way to healthcare insurance coverage. I am very, very confident that if we have a cell therapy that works, that there is a value proposition that it'll be covered by insurance companies. And we are already teeing this up with FDA and with insurance companies. I can't get into the SEMA discussion specifically that we've had, but one of the early discussions with them was around the business model and ensuring that payers will pay. The good news is every payer that, and I've spent a lot of time on this over the last 15 years, realize that diabetes costs a lot of money. Insulin costs a lot of money, sensors cost a lot of money, pump costs, but even more so, emergency visits and complications cost a ton of money. So anything that we can do that there's actually an economic argument that's pretty easy to make, and then it just becomes a business model for companies to take advantage of. So that's something that we're very, very focused on, and I'm hugely confident that when, I'm not going to say if, that when these guys are successful, that we'll see this commercialized and reach the hands of people. Other questions? Kelly? Do you want to yell it out and then I'll just repeat it?
Yeah, thank you so much. This is really so exciting to see. When I saw the announcement, I was reading it to my kids and was just kind of weeping. I mean, it is amazing what JDRF is driving forward. And I was just curious if you could talk a little bit about the two universities working together and how that will work with JDRF, what JDRF does. Aaron and his, is it 20 PhDs in headquarters, you know, all of your amazing relationships at FDA, all of your amazing relationships in industry. Like what are all of the extra great parts about getting to work with JDRF in a really organized, structured way?
We read each other's thoughts, so we were going to say the same thing. Dr. Hebrock directs the center, Diabetes Center at UCSF, and I direct the Diabetes Center at Stanford. And so we have experience in coordinating complex multi-investigator groups around diabetes or other things. And so to ensure collaborative alignment and things like that, we have, as part of the structure of this Center of Excellence, something called an administrative core, which is pretty mundane sounding, but it encapsulates how we would oversee things. It has program managers. We've already built, and we haven't quite rolled it out, but we've already built a coordinating website that just lacks a few details, but it should be live soon. And the plan is to start to meet regularly with each other. The first meeting is already set for October 7th. It's a chance for the scientists to talk about things in their own, pretty much in their own language. I think it would be a little bit abstruse for some people, but there will be people from JDRF and the local chapter there. There will also be meetings regularly with either video conferencing or on site, the people from Manhattan and to see what progress we're making toward our milestone. So I hope that partially answers your question.
So it's a little bit, it's a fine line between being too much involved in something and not being involved at all. And this is something that we're going to try to figure out too. So we're hoping, as Song just said, we have the first meeting in October, so in a month from now, where we're going to have everyone who's involved in this is almost get to know each other. And we're hoping that usually the scientific interest is going to predominate there. What I mean by that is that someone is going to see something and say, hey, this is really cool. You know, I have something that can build on that, or we can use this information, or you should try this. And so that we're getting to the point that there are some natural interactions that are going to be forming on top of the structure that we're trying to impose on it. So the hope would be that the science is going to be the main driver, and the JDRF, of course, is going to be involved in this and helping us. But almost everything we do in my lab and in the labs of my colleagues, as well as our friends at Stanford, is directed towards either the beta cell or the immune system, and therefore has implications for type 1. So I think this is going to be good.
It's great. I'll just, and I see another question, say, from the JDRF perspective, sometimes people say, what are the scientists at JDRF doing? And one of the things that we try to help to do is provide the broader contextualization of the research, meaning, and remember, we're talking about Stanford and UCSF, but this is a big ecosystem. And Stanford and UCSF in this center will not exist in isolation. We have an encapsulation consortium, for example, that has 40 members. Biomaterials people, gene editing people, Novo Nordisk, J&J, ViaCyte, all weighing in and trying to help these fields move forward. So there's competition, but there's tremendous collaboration. FDA and NIH and Helmsley. And I think that's an important lens that the JDRF scientists bring is, what else is happening there? And making sure that's incorporated. And it's our goal is to be supportive, providing financial resources, providing some intellectual resources, providing the collaboration opportunities, providing a baton handoff for companies who are interested. So that's why I'm super excited is this is a powerhouse team. The JDRF scientific team will hopefully bring those other resources that exist all around the world to try to help this project be successful. So I know you had a question back here.
Yeah, so earlier in the summer, there was a lot of hype around like the insulin price, reduction act. I think it was introduced by Susan Collins, and I haven't heard anything since. Is that real, or are we getting BS'd?
No, I don't think there's any BS happening here. I think the challenge is the US system is broken. And fixing it through legislation in Congress, through the executive branch and the Trump administration is very, very difficult. I can tell you that this has dominated my time in Washington. I've testified 3 times on Capitol Hill. We've been calling for price reductions throughout the system. So there are a number of folks working really, really hard to try to fix this. And I can honestly say, and people are gonna scoff at this, I met with the CEO of Novo Nordisk. The companies desperately want out of this problem. And you would say, how could they not? Well, they have all the power to do it. It's actually, it's not so easy because of the way our system is set up with all these intermediaries. So I can tell you, JDRF is fully committed to seeing insulin price be reduced. The fact that when I'm in Seattle, I could cross across into Canada and pay a tenth is an unacceptable situation. So Susan Collins, who's the head of the Diabetes Caucus on the Senate side, has introduced legislation. There's House legislation. There's all sorts of stuff happening. The unfortunate other side is to bring this home is difficult because this is not just insulin. This is all drugs. And there's a lot of money at play, and it's so I wish I had an answer. I can tell you that we're going to fight until there is a solution. Karen? All right, we'll let our volunteer of the year, and I know you've been patiently waiting, so I'm gonna do CEO's prerogative and have 2 last questions.
Can you talk about one of the key points of the center in that the funding mechanism is different than the traditional grant funding, and how this might afford more flexibility and enhance better science by allowing the researchers and the brilliant minds to actually be in the labs?
Yeah, so one of the things, and Matthias was part of a committee that helped advise us on how we're always looking to do better. You know, when I took the job as CEO, I gave the anecdote that I'm a huge believer in continual improvement. And my anecdote was every time I mow my lawn, I try to figure out there must be a better turn on my tractor that I could do it a little bit better. And I think when we are always looking at, can we fund better? How can we help move faster? And Matthias was very generous with his time to help give feedback that if we did some of our funding, that it could be more efficient. It could have the investigators spending less time at the typewriter, or now I guess typewriter is absolutely, the PC or Mac, and more time in the lab. So this funding is intended to have less administrative burden and more time, you know, being a dialogue on where is the science flowing. Because all of us, I was fortunate to work in the lab for many years, know that science is a fluid thing, and we pivot and we learn. So I don't know if you guys, hopefully you feel that we're making some progress.
Sure, we do. But the other thing I think is, and probably what you're getting at too, is that we are hoping to raise more funds specifically in our neighborhoods that can flow into the center. that would be something that we would love, because at UCSF, and I'm pretty sure Song would say the same thing, we got the center that's fantastic, and it funds a tremendous number of people, but we had to leave some people out. Some ideas that I already know, people come to me and say, "Why am not part of the center?" Well, the reason was it would get too big and we don't have the funds to support you. But being able to even grow this more, that's what I'm finding so excited about this. I think it would allow us to accelerate this more by bringing even more ideas to the fruition.
We don't look like it, but we take risks.
Speak for yourself.
In the lab. And it's hard to take risks on a 1 or 2 or 3 year time frame. We have 5 years of funding through this mechanism. That's an important thing to state. And although it's not a huge risk, that means we can invite fresh ideas and experience into the risk-taking pool. Kyle Lowe, who's an assistant professor and colleague of mine at Stanford, who's sitting here, and you'll meet later on, is someone we tried to bring into diabetes research. This is, I think, one of the first, if not the first, funding support streams to support that. He is one of the he's one of the shining new recruits we have. He's been at Stanford for 2 years, and it's just so exciting to have him be thinking about cell replacement and working with Matthias on programmed differentiation of cells. So that's partly the answer, the stability of that. The other is, I think, the administrative burden and the relative freedom to pursue what we think are the best ideas, knowing that we need to be aligned toward ultimately clinical trials. And that, I think, is also enabled by this, I wouldn't call it funding flexibility, but a kind of trust in the people as much as the projects.
So we're going to do one more question, and know that we're going to meet downstairs, and we'll all be here for folks to talk to and ask questions that we couldn't get to, but I know you have been patiently waiting. So last question.
First off, happy birthday, Dr. Kim, and thank you for sharing your special day with us. My question has to do, gets back to Howard's initial question, and then Aaron's talking about affordability. In the case of individualized cell replacement, so where you're taking a cell from somebody's body and then creating pluripotent cells from that, I would really love to hear you address how that is going to be commercialized.
Yeah, I can probably do this. We're not going to do this because, as you point out, this would be just prohibitively expensive. That's why I danced around the issue. But so when I said immune cloaking, that's essentially why you would take your own cells, because your own cells are being recognized by your body as belonging to you and therefore not being attacked until likely they turn into a beta cell, right? When essentially the immune system says, well, voila, there's one of those, and I'm going to take it out. So even if I take an IPS line from someone who has type 1 diabetes and make the most beautiful beta cells out of it, in the absence of instilling intolerance, or what Song was talking about, or what Jeff Lewson has been working about, this beta cell would be destroyed. So it's not that helpful for this particular disease, at least what we know as of today. The other thing is, as you point out, it's just too expensive. So if we can cloak a cell, we can get the same benefit. That's the idea behind it. That essentially then could be given to a number of different patients. And there are calculations out. I don't have them right now in my head. That people think several hundred lines would be sufficient to essentially meet the immunological responses of a vast part of our population. So yes, you're right. We cannot generate single lines. At least I don't think we can. Sorry.
Is there room for the side? No.
Well, no. We're still working with IPS lines. We work with IPS lines. The reason why we work with IPS lines has to do that there are no ethic considerations. You don't have to destroy a human embryo. You essentially can use somatic cells from someone who is in this room, for example. But for a company to take your cell then generate different lines, make sure that they have high quality. Now we learn that at a certain point there are mutations in the mitochondria. If you're above, let's say, 45 or 50, the IPS lines you're generating from you are likely going to be not as good as the ones that you would have from a baby. So that would exclude a significant portion of our population right there. And then essentially after testing, doing quality control, generating the cells and so on, I think it is prohibitively expensive.
So I'm just maybe to reiterate what Matthias is saying is the bulk of type 1 people we believe could be cured through either through cell lines and through a limited number of cell lines that we don't need to go to individual cell. And that will make for a business model that works, but also scientifically for the population of type 1 people, we think that that would work.
When you get a red cell infusion in the emergency room because you had something happen, those cells are not matched to your genetics. They are matched to the blood incompatibility or compatibility groups, but they're not a perfect match. So the concept of banking cells and tissues already been established. So I think that's what they're talking about.
Well, all right. Well, gentlemen, thank you so much. This is an exciting day. I always say that the best part of my job is I get to work with incredible people, and Sung and Matthias, you're two of the incredible people I get to work with. But we also have incredible staff. We have incredible volunteers. You know, they always say it takes a village. This is San Francisco is an example of how this partnership amongst the community is driving our mission forward. So we're gonna reconvene downstairs. I look forward to talking to you individually, and thanks again, gentlemen.
And thank all of you guys. Thank you.